Welcome to Web Handling. My name is Dave Roysum. I am very excited to continue a new mini-series on old topics. That is, conference papers that I gave some time ago. A long time ago. Why would you want to watch something old? My first answer is that it is still timely today. In other words, the essentials have remained unchanged. My second answer is that YouTube is free. If you want more current or more complete information, you would need to buy one of my books or attend my 2-day winding school. By this time in my career, I had developed a pace and a voice. By a pace, I mean one semi-decent technical paper per year that I've continued for 30 years. By voice, I mean an originality where each paper was usually unrelated to any that I'd written before, and usually one of a kind in our industry. Again, the video tools I had to work with 30 years ago were not great, so I apologize in advance for the VHS tape quality and the dry, hired voice. Still, I think this will be worth your while for two reasons. The first is that it is a pretty complete listing of commercial roll quality measurements. The second is that it shows a methodology to statistically evaluate how good a roll quality measurement instrument is. In other words, how to test the tester. This is really important, as measurements are very expensive and can be really expensive if you take inappropriate action on them. A consumer error is assuming the roll is good when it is not. A producer error is assuming the roll is bad when it is in fact good.
In the next few minutes, we will describe several methods of roll structure measurement, how they operate, how to evaluate them, and finally we will set up necessary ingredients for a roll quality program. There are many quality issues in the finishing room that must be addressed so that customer requirements are met with maximum efficiency. These include minimizing roll structure defects, such as bursts, loose cores, and starring, by optimum choice of torque, nip, and tension programs. Torque, nip, and tension, sometimes called the TNTs of winding, are the key controllable parameters we have to improve roll quality. Roll geometry defects are deviations of the final roll shape from a cylinder of the customer-specified diameter and width. Web properties also have a large effect on roll quality. Unfortunately, seldom in practice are web properties a controllable parameter for improving quality, because nominal properties are often specified by customer requirements. Similarly, though variations of properties about the mean are often as important as the mean itself, these are determined by the paper-making process upstream. The old saw, "You can't make paper on a winder," is a succinct expression of the fact that many roll defects are strongly influenced by web properties which are not controllable at the winder. While there are many quality issues, we will concentrate on the roll structure aspects of quality control. Roll structure is defined as the interlayer and machine direction stresses inside a wound roll. Though we often speak of the hardness, tightness, and density of rolls, structure is better described in terms of web stresses. We need the interlayer pressure or radial stress to be high enough so that the roll is structurally stable against loads in subsequent handling, shipping, and unwinding processes. The machine direction or tangential stress must be high enough to avoid creping, buckling, and starring, while not so high as to cause bursts or tears. It is important to understand that the structure of a roll varies along its width, through its diameter, around its circumference, and with time or added wraps. Therefore, a complete description of the machine direction stress, for example, would require a 5-dimensional plot. However, it is customary to profile a roll after it has been wound and assume that variations around the circumference are minimal. This reduces roll structure to a three-dimensional plot as a function of roll diameter and cross-machine position. Unfortunately, any single roll structure measurement method is presently limited to either profiling through the diameter or across the width, so that a complete picture of structure is not easy to obtain. There are many ways to measure roll structure that are sensitive to changes in web stresses, which could be used in a quality program. The principles available to indicate conditions that are associated with the potential for roll defects include impactors, which measure hardness, such as the billy club, row meter, and Schmidt hammer. Friction-based measurement of interlayer stress, such as the core torque, pull tab, and Smith needle. Strain-based measurements of machine direction stress, such as the Cameron gap and J-line. And finally, the density analyzer. The row meter is a handheld impactor measuring the peak deceleration of a small hammer striking the rewound roll. Though similar in principle to the billy club, it has the distinct advantage of being able to quantify roll structure. Quality control requires numerical measurements of relevant variables. The Schmidt hammer is also a handheld impactor. However, it measures hardness in terms of a coefficient of restitution. While the row meter is predominant for paper and film in the United States, the Schmidt hammer is more common in European paper mills. The core torque test can measure interlayer pressure at the core by fitting a torque wrench with a chuck and applying torque until the core slips. From the value of slipping torque, coefficient of friction, as well as the core diameter and length, interlayer pressure can be calculated. This simple test can determine if a sufficiently tight start was applied on the winder to prevent telescoping during unwinding by your customer. The Smith needle can infer interlayer pressure at any radius at the roll ends by measuring the insertion force required to penetrate a needle between two adjacent layers. Though the Smith needle and core torque test are both based on friction measurements, the torque test may be more consistent because of the much larger measurement area. The Cameron gap test, which is a Tappi standard test method, measures the machine direction strain on the outer layer of a roll. This simple test requires only a knife and a scale or 10 times magnifier with reticle to measure the gap, and a tape measure to measure roll diameter. However, it yields only a single value, which is the average stress across the width at the roll's outer diameter. Consequently, it gives no profiling information about the roll beneath the outer layers unless the roll is slabbed down and more measurements made. If we strike a radial line on a winding roll, we observe that the outer end may quickly skew in the direction of the wind as interlayer slippage occurs. The principal mechanism of J-line deformation is the relative slipping between layers of paper due to repeated passage of a nip roll in close proximity. As additional wraps are added, J-line movement slows because the nip affects primarily the current outer layers. J-lines are quantified by the angle and depth of the deformed line tip. The magnitude and roughness of J-line deformation is a useful indicator of the propensity to crepe wrinkling on lightweight grades. The density analyzer is a recent innovation in roll structure measurement. This computer-based instrument has at least 2 encoders that are attached to the core and a roller or drum which travels at web speed. The pulse output from these encoders are counted by counterboards which interface to a computer. The counts are then used to calculate the density of the outer layers during winding or unwinding. Any sufficiently large increase in winding stress or tension will result in increased density readings. The density analyzer is one of the truly modern and automated test methods for roll structure analysis. The wound-in, wound-off tension, or Whitwatt winders, are single-drum rewinders which were specifically designed for Pfeiffer's classic work on tensions during winding. The Whitwatt winders are able to measure machine direction tension with great precision and resolution. Unfortunately, there are only 2 of these lab instruments, so this type of testing is not available for general production use. However, rewinders of any type can be used for detailed and careful testing of rolls in a mill environment. As the roll is unwound slowly, it can be profiled across its width and at various diameters to give a complete three-dimensional picture of the roll's structure. For example, a row meter could take readings at 1-inch increments across the width of the roll and at 1-inch diameter increments as the roll is unwound. This rewinder testing can be augmented with other test methods as well as close visual inspection. With so many methods available, we would like to evaluate each to find the best for our particular finishing room situation. Listing our various classes of methods, which again include impact testers for hardness, friction-based measurements for interlayer stress, strain-based measurements, the density analyzer and Whitwatt. We can judge them with regard to several important characteristics. One of the primary differences between the methods is the ability to profile a roll either across the width or through the diameter. As can be seen from this chart, the impact testers can give readings for any arbitrary cross-machine location, while the others can only give a single value corresponding to the edge or average across the width. Thus, the impactors are better suited to diagnose problems such as corrugations, which result from non-uniformities in caliper across the web. Unfortunately, the impactors and the camera and gap can't profile at different diameters unless we stop the roll during winding or unwinding to take a reading. Conversely, the remaining methods easily give readings at different diameters, which makes them better suited to diagnose problems associated with improper roll structure parameters, such as the programming of torque, nip, and tension. Accuracy and resolution are vital issues that are covered in much greater detail in the accompanying paper. We must be able to resolve roll structure changes accurately with a minimum number of measurements so that our testing costs are also minimized. In this era of computer automation, manual measurements written down in a form on a clipboard are being replaced by computerized data acquisition. Similarly, data evaluation and report generation should be performed by programs or spreadsheets rather than by pencil and calculator. The reason for these changes are not just a preoccupation with technology, but rather to improve our competitive position. Automated testing and report generation, if done properly, can tremendously reduce labor costs, scrap, and culled rolls. We also want our test method to measure values as closely related as possible to the fundamental roll structure variables of interlayer and machine direction stresses. Of the methods, the camera and gap and the Whitwatt yield strain and tension which are closely related to stresses, while the impactors measure values only distantly related to stress. Obviously, we should avoid testing that might damage the product, such as is possible with the Smith needle, camera and gap, and J-line. Ease of use is important not only to the roll inspector's morale and performance, but also to reduce labor costs. The greatest factor in testing costs is the labor required to obtain sufficient readings to resolve and diagnose problems, while test equipment costs are usually incidental. Since labor is the primary ingredient of testing costs, it is important that we choose a method that is able to resolve changes in roll structuring with the least number of readings. This can be done by winding a large step change in the TNTs at a certain diameter. We take several readings on each side of the step to determine if this large effect can be detected with the various instruments. Surprisingly, several methods in common use are unable to detect even the grossest roll structure changes, such as sudden steps and splices. Obviously, those methods have no use whatsoever in quality control testing, which seeks to detect much more subtle effects. To determine the number of measurements needed to resolve a certain magnitude of roll structuring change, we need to know the means and standard deviations for the measurements on each side of the step. From these, we can calculate the standard error of the estimate. the z-statistic, and finally the number of measurements needed to obtain a specified level of accuracy to a specified confidence level. Though this testing is somewhat time-consuming, it shows that not only are there orders of magnitude of difference in the resolution of the methods, some of the worst can give absolutely meaningless values. It is tragic that many diagnostic conclusions have been made in error because the data was as statistically significant as throwing dice. I have personally witnessed many expensive decisions such as role rejection and machine selection based on worthless data. Some instruments are better than others for our application, and some techniques are better than others. However, we will never know unless we evaluate them objectively with statistics. We can implement a roll quality program which can avoid shipping defective rolls as well as preventing them from occurring in the first place by following a simple procedure. First, we rank roll problems by frequency, or preferably by total cost. This enables us to determine where to best spend our efforts for maximum gain. Next, we select a measurement method that is either most sensitive to roll structure changes or most sensitive to our worst problems, using similar techniques as discussed earlier. It should be apparent now that if our defects tend to occur in the roll's interior, we will not be able to detect them from measurements at the roll's outer diameter. The optimum sample frequency varies considerably depending on the demands of our particular grade. This optimum may be when problems occur, randomly selected rolls, or every roll. The optimum is determined by the minimum sum of the costs of testing plus the costs of roll defects that are preventable by testing. Sample size should be selected on the basis of how many measurements are needed to achieve a required resolution with a specified confidence level, and is independent of our choice of sample frequency. A typical sample size might be 5 measurements, throwing out the high and low, and recording the mean of the remaining 3 measurements as a single data point. We need to develop a standard recording medium, which might be a form, or better yet a computer file read by a program or spreadsheet. Simply taking data is not enough. We must analyze the data so that appropriate action can be taken. To this end, statistical techniques are absolutely required for even the most minimal roll quality program. The uses of statistics, as well as the dangers of making conclusions without them, is described in more detail in the accompanying report. If roll quality measurements are made frequently, a computer program should be written which condenses measured data into meaningful roll quality statistics. To prevent unacceptable rolls from being shipped to our customers, we must quantitatively define what acceptable means and find a method that can reliably distinguish between acceptable and unacceptable rolls. Reliable acceptance criteria minimizes false positives, which means shipping bad rolls, and false negatives, which means rejecting good rolls. Obviously, it is preferable to prevent defects from occurring in the first place rather than detection after the fact. This requires a considerable knowledge of the process and product, a large volume of data, and most importantly, a statistical correlation between controllable variables and the frequency or severity of defects. To minimize the volume of unacceptable rolls produced before corrective action is taken, measurements should take place at the winder. This allows diagnostic procedures and subsequent corrective action to take place quickly. Ultimately, the goal of any roll quality program goes far beyond merely taking and recording measurements. We strive to make consistently better rolls. We know how. Let's do it.
This is such an important topic area that I've returned to it 3 times again in my career. The first 2 times were as chapters in 2 of my books. My Winding Machines, Mechanics, and Measurements book, co-authored with Dr. Good, gives 100 pages of detail on the roll measurement area. I also teach 2 modules on the topic in my advanced 2-day winding class. Thank you so very much for watching this module in my Plant Practical video series. Stay tuned for the next clip where we provide an overview of winding models, measurements, and diagnostics. See you next time.